This is the unit, last unit, second part. So here we all know magnet. We have seen, right, magnets. Have you seen these magnets?
Yes.
So what are the applications? Why we are interested to learn about this magnetic materials or magnetism? Where we will use these magnets? What are the applications? You are regularly seeing these magnetic materials, right? So where we are using these magnetic materials? You know, many applications.
TV sound boxes.
Yeah, the speakers we use. Okay, speakers and this scanning endoscope and this thing are there, no improvements. There also will use strong magnets. Okay, strong magnets will use there also. Medical, okay, strong magnets will use. And also in nowadays they are on the speed trains also. They will use, they will put the magnetic tracks. From there you can send the train. Because of this repulsion of this train, because of repulsion of this magnetic track, they will push the train very speed. Okay, that type of applications also coming. And many we are using many places these magnets, right? Okay. So so how this magnet is forming, what are the applications, how this different type of magnets we are using? Okay, that we will see. Okay, generally magnet means it is a magnetism means it is a nature of attraction or repulsion. Okay, it will maybe some objects maybe attract and repulse. Okay, that is the thing. Okay, generally we will see that one. Okay, generally if you see any magnet, there is a north pole and south pole. North pole and south pole. This is the main property. There is no monopole is not exist. Okay, monopole will not exist. Okay, this is not possible. Okay, only two poles. Always there is a two poles, north pole and south pole. Okay, in the south pole always this magnetic lines, whenever if you see electric field, here plus charge and minus charge, this plus charge and minus charge, always field lines will pass through plus to minus, right? Plus to minus. In electric field, electric field lines will pass plus to minus. Here how it will pass? Which N for north and S for south pole, north pole and south pole. Always magnetic lines of force will pass north to south, north to south. Okay, these are what we are calling magnetic lines of force or magnetic field. Magnetic field, or we can say, okay, like this. Always north to south, and if you see it like this, you will see. Okay, here also magnetic lines of force always north to south, north to south. And so here also there is a two poles will exist. Okay, two poles will exist. These two poles are equal and opposite. Equal and opposite. These two poles we are calling magnetic dipole. What we are calling? Magnetic dipole. Okay, magnetic dipole. So before going to this unit, so shall we discuss how the magnetic field is coming within a material? Suppose if you take any material, suppose you take a iron, suppose iron. So this iron, how this is attracting the objects, some other objects or some any objects. So how it is attracting or how it is repulsing? What are the reasons for magnetic field in a material? So please tell me what are the reason. Suppose you are producing electric field. What is the reason to produce this electric field? Charge in a material, any charge, positive or negative charge, is the main reason for producing the electric field. Okay, what is the reason for producing the magnetic field in a material? Please tell me, do you know answer? How we are getting the magnetic field here? Anybody please answer this one? Don't know? Okay, if you don't know, no problem. So generally we know this is a positive charge, this is nucleus, and electrons will revolve around the nucleus. This is we know, right? This is atomic structure we know. So when generally the origin of the magnetic field, mainly three regions are there. First one, orbital motion and orbital motion, orbital motion of electrons, and second one, spin motion of electrons or spin motion or spin of electron. Third one, nuclear motion, motion nuclear motion of nuclear motion nuclear motion of uh, nuclear motion of this center. Okay, so generally electrons revolve around the nucleus, like our planet system, earth and all planets. This is sun, and all planets will revolve around the sun. Okay, all planets, like all planets will revolve around the sun. Here also electrons will revolve around the nucleus, and nuclei also revolve around in themselves. Okay, so here it will revolve themselves and also revolve around the nucleus, like a planet also. Suppose if you take earth also, earth will revolve themselves and also revolve around the nucleus. Okay, so earth is rotate themselves, and also it will rotate along the orbit of the sun. Okay, same thing, electrons also revolve themselves and also revolve around the nucleus. Okay, because of this orbital motion of electron, there is a some magnetic field. These electrons act as a magnetic dipole. Electrons act as a very tiny magnetic dipoles. Because of this magnetic dipoles, there is a magnetic field in a atom. Next one, spin motion of electron. Okay, spin generally around, they will spin also. Okay, that means themselves they will revolve, themselves they will rotate. Okay, so this, because of the spin also, uh, there is a magnetic field. And also finally, nuclear motion. Okay, this center will also revolve themselves, like sun also revolve themselves, right? So itself, sun also itself, they will rotate. Okay, self rotation plus self rotation. Sun is also having self rotation. Similarly, this nucleus is having self rotation. Because of this self rotation also, we are having some magnetic field. But among this all, this spin, because of this spin, we are having higher magnetic field. This spin is mostly influencing the magnetic field compared to orbital and nuclear spin. Okay, these are the origin of the magnetic field. Suppose if you take, so here we have a different type of magnetic materials, right? Dia and para and ferro. Have you heard about this one? Dia, para, ferro magnetic materials.
Yes, sir.
So here see, okay, thank you. So here suppose if you take any atom, if completely filled, okay, completely filled that electrons, here spin is zero. So that act as a diamagnetic material. Suppose here some is partially filled. Suppose if it is partially filled, that will show as a paramagnetic field, magnetic material. Or some of the again partially filled, 2 3 orbitals will partially filled, one orbit, this is another orbit. Okay, here two orbit, let's take example. Here two orbital partially filled, so here spin is more compared to second case. Here spin is off, here spin is 1. Okay, so here spin is high, so it act as a ferromagnetic material. Depends on how the electrons are filling in a orbit. So according to that, the spin also changes. Okay, according to that, spin also changes. If it is completely filled, the that elements act as a diamagnetic material. If it is partially filled, that act as a paramagnetic material. If it is more number of orbits are partially filled, that act as a ferromagnetic material. So ferromagnetic material strength, strength is very high compared to para. Dia is almost just like non-magnetic, just very less magnetic material. Temporary magnetic field will be there here. Suppose if you apply some external magnetic field, then only it will show some very less magnetic field. But ferro, like iron, if you take iron, whatever we are using, if you take any iron material, it will attract very easily, or it will repulse very strongly. That type of behavior elements will have. So mainly the origin of magnetic field is mainly due to three reasons. One is orbital motion of electron and spin motion of electron and nuclear motion of the center. Okay, nucleus or nuclear motion of nucleus, you can say that. Okay, among these, because of the spin motion only, dominant process of producing the magnetic field. Suppose if a element, if you take any element, if all electron field completely filled, that act as a diamagnetic material. If it is partially filled, one or two shells, that is act as a paramagnetic material. If it's more number of orbitals or more number of shells will partially filled, that act as a ferromagnetic material. Okay, so here ferromagnetic materials very strong magnet, they are having strong magnetic field, they will strongly attract and strongly repulse. Okay, ferro para is little bit less compared to ferro and dia is more less compared to para. Okay, these are three type of classifications are there. Dia, para, ferro depends on magnetic field or magnetic strength. Okay, so this is the origin of magnetic field. Suppose if anybody asks you, you tell these reasons. Okay, so now we'll come to definitions. Okay, magnetic dipole moment. Suppose here we always have a north pole and south pole, north pole and south pole. These two pole, like in electric field we have positive and negative field, right? This is what we are calling, these two positive and negative charges we are calling dipole. That is electric dipole. Here also we are having north pole and south pole. These two poles we are calling magnetic dipole. Okay, dipole means two. Di means two. Di means two. Pole means two. What do you say? The opposite terminals, or you can say. Okay, these two poles, two opposite and equal and opposite poles. Okay, this is magnetic dipole. So what is the magnetic dipoles you will measure in pole strength? What is the units are pole strength? I will measure pole strength, units are ampere meter. Ampere meter, these are the pole strength. Next one, magnetic moment. Magnetic moment, there we have studied electric dipole moment. Here also you can write magnetic dipole moment. Okay, magnetic dipole moment. What is the definition of electric dipole moment? Please tell me. Here plus charge and here minus charge. What is the electric dipole moment? Small mu or small p or mu, whatever we have discussed in previous classes. What is the electric dipole moment? Please tell me, answer this one. I will forget. What is the magnetic dipole moment? Electric dipole moment. Please tell me, answer this one. I have given clue also here. What is the electric dipole moment? Can you hear me first of all? Please answer. Now you tell me. Are you there at least? Finally, are you there? Are you listening at all?
So,
If you don't know, please answer. Tell me. You don't know.
charge into distance.
Yeah. This charge into distance is electric dipole moment. So this is already I have given clue and you are not answering. This is just one day before class. This one. Okay. Here, electric. If you say, if you read electric this dialectic, this magnetic materials also same definition, similar. Okay. Need to worry. Okay. Here, electric dipole means charge into separation between these two charges. Here also magnetic movements means, suppose here north pole and here south pole. The distance between uh, pole strength and the distance between these two poles, these two poles. You can take L or you can take 2L, whatever you can take, it's not a problem. Okay. So here also you can say capital M is equal to, if you take 2L distance, 2L into M. M is the pole strength and distance between the two poles, that is given by magnetic dipole moment. Like electric dipole moment, the pole strength and the distance between two poles, this gives the magnetic dipole moment. Here length is the meter units, magnetic pole strength units are ampere meter. So total units are ampere meter square. Ampere meter square units for the magnetic dipole moment. Here coulomb meter. Here coulomb meter. Electric dipole units are coulomb meter and magnetic dipole moment units are ampere meter square. Ampere meter square. Okay. Now next one is magnetization. Okay, next one is magnetization. Or you can say magnetization, you can write this is a process of converting non-magnetic sample into magnetic material. Or you can write this one. Okay, magnetic dipole moment per unit volume also you can write. Magnetic dipole moment per unit volume also. There also we have written polarization, capital P, what we have written, dipole moment, electric dipole moment for unit volume. Here also magnetization you can write I. Okay, you can write I. Okay, magnetize, or you can write here. I will give the term this one. Okay, magnetization for magnetic field for or magnetic dipole moment for unit volume is gives the magnetization. It will gives the how we are converting non-magnetic material into magnetic material. Okay, that is the definition. And magnetic field induction. Okay, magnetic field induction or magnetic flux density, or you can say magnetic flux density. This is also important. Few terminology is very important because so without this terminology you cannot understand. Okay, you can write here B, magnetic field induction or flux density. Okay, that means what? Here flux density, electric field density means what, or charge density means what is the definition? Charge density sigma. What is it? Electric charge density or volume charge density. This is surface charge density, volume charge density. What is the definition here? Hmm? Charge density. Here charge per unit area, that is charge density. Here flux density is there, definition. In the question only you will have answer. Okay, that means flux per unit area. Okay, magnetic flux per B is equal to magnetic field induction or magnetic flux density, magnetic flux per unit area. Okay, magnetic flux, what are the units? Magnetic flux Webers. Okay, Weber, and area you know, meter square. Weber for meter square you can write means Weber for meter square you can write Tesla. Okay, you can write Tesla. This is magnetic field induction or magnetic flux density. Now we have defined this magnetic flux density, that is flux per unit area, flux per area. So what is the flux now? What is the magnetic flux? Anybody answer this one? Magnetic flux. How you will define this magnetic flux? Suppose you have a area, this much area. So in this area, how many magnetic field lines pass through this area gives the magnetic flux. Okay, how many field lines pass through this area? This is area we are taking some area A, any area you can say area. In this area how many magnetic lines are passing perpendicular to this area gives the magnetic flux. So here definition is flux we have defined. Flux means magnetic flux means how many number of magnetic lines of force are passing through the area perpendicular to particular area is giving magnetic flux. Here very simple. Number of magnetic flux means definition, number of magnetic lines of force passing perpendicular to the particular area. Passing perpendicular to the particular area is giving flux. Now magnetic field induction or flux density means flux per unit area. Units are Weber per meter square, or you can write E equal to Tesla. This Weber per meter square equal to Tesla, 1 Tesla. Okay. So this is the thing, and or you can write you can define this way also. You can define this way: magnetic force for acting as a magnetic force that is experienced at a unit north pole, unit north pole, or you can unit north pole at a point in a magnetic field. That is also you can define. B is equal to F by M. Okay, Newton for ampere meter. This way also you can define. So you can define magnetic force experienced by a unit north pole. Suppose you have a magnetic field here. Suppose if you keep any small magnet here, this is external magnet, and you put a small magnet. Okay, here how much force is here, north pole and south pole here. So how much force is experiencing this north pole? That is gives the magnetic field induction or magnetic field flux density. Okay, that way also you can define. It's not a problem. Okay, next one, magnetic field intensity. Magnetic field intensity, you can define this one as H. And magnetization we have discussed, right? Magnetization, that is you can identify as H, or magnetization or intensity of magnetization. Second, that is you can intensity of magnetization is given by term I. Okay, here magnetic field intensity is given by H. This will gives the, how you will define this one. So magnetic field intensity is given by 1 by mu times of 1 by mu times of magnetic field flux density. Magnetic field flux density. This is very easy. Here also you can write ampere. What are the unit? This Tesla for, or you can write ampere turn per meter. You can, these are the units. Okay. Ampere turn per meter. So here you can write here like this. So this is how you will define magnetic field intensity. Magnetic field intensity is 1 by mu times of magnetic field flux density or magnetic field induction. Okay, now here mu is the what here? Permeability. Okay, permeability, that we will discuss now. Okay, permeability here, see. So B is equal to what we have written, H is equal to B by mu. B by mu. Okay, here mu is the permeability, like that magnetic permeability. Okay, it gives the how easily our magnetic field is magnetizing, or any material is magnetizing. Okay, after applying some external magnetic field, how easily the material is magnetizing. Okay, that will gives the that information. Okay, here you can write mu is equal B by H. B by H. B is the, what is B here? What is B here? What is B and what is H? Magnetic. Yes. Yeah, magnetic field induction and magnetic field intensity. Okay, here units are Henry per meter. Okay, units are Henry per meter. Which is called, it's a ratio between magnetic field flux density or magnetic field induction to magnetic field intensity. Okay, that is very easy definition. Okay, this will gives the how easily material is magnetizing. How easily material is magnetizing. Okay, so here relative like relative dielectric constant, here also relative permeability also there. It is given by definition medium permeability to space permeability, free space permeability. This is the definition of relative permeability. Relative permeability mu r is given by medium permeability to free space permeability. Okay, mu zero values you can write the units are cancelled out, those total units are no units are there. Here what mu 0 value, it is constant value 4 pi into 10 power minus 7 Henry per meter, Henry per meter. This is the constant value. Okay. Free space or vacuum permeability. Okay. Now we have defined permeability. Next one, susceptibility. This is also one of the important parameter. Mu mu, this is chi. Okay, this is susceptibility. Permeability, susceptibility are main important parameters to characterize the dielectric materials. Okay, like dielectric constant, we have studied this one, and this is like dielectric constant. Here also some constants are there. Depends on these values, we can estimate the magnetic field. How which type of magnetic field is one, which type of magnetic material. Here also the magnetic susceptibility is given by chi. So this is ratio of magnetization to magnetic field intensity. Chi is given by I by H. I by H. This is I means intensity of magnetization or magnetization. H means applied magnetic field intensity. This is applied field. Okay. If you apply some external field, how much magnetic field is developing? That is the difference between these two terms. Here also we are talking intensity. Here also we are talking intensity of magnetism. So this is applied field. H means applied field. Suppose you have applied here some field here. If you apply some field here, how much magnetization is developing, how much intensity of magnetization is developing on the material. Suppose you have a material here, you are applying some H field, that is like just take a 10 10 ampere turn per meter. You are applying 10 ampere for turn meter. So how much intensity or how much magnetization is developing within this material after applying some. Suppose you have a material here, you are applying some external electric field. So how much field is generating within this material. Okay, here also same thing. If you apply some external magnetic field, how much magnetization is developing. Here you can say this term intensity of magnetization or magnetization. You can write intensity of magnetization or simply you can write magnetization also. Both are okay. But don't confuse with H and I. Here applied magnetic field intensity means H. Applied means we are applying some external field. Okay. That is the difference. Okay. So it gives the ratio between I by H or intensity of magnetization to external applied magnetic field. Okay, here also no units. Permeability, no units, and susceptibility also no units. Okay, this is ratios. Okay, ratios, so no units, these two. Okay, now these are the definitions. You got it right, definition. Do you understand the definitions? Any doubts in this
Yes.
definition? So after this one, just go through definitions. Once you will be clear with the definition. Now we'll go to the dia, para, ferromagnetic materials. We have depends on this magnetic strength. We have divided into three categories: diamagnetic and dia, para, and ferro. Dia, para, ferromagnetic material. Dia, para, ferro. These are three different kind of materials. Depends on magnetic strength or pole strength.